Hello, everyone. In this episode, we'll talk about TurboQuant. Um, some of you may have heard that recently there was a paper published by Google and some researchers, and it's called TurboQuant, and it actually shocked the stock market. It was a way to economizing, storing, saving memory during the LLM computation, and it basically had a strong impact in the industry. So let's talk about what was the big deal about it, what it does, and how it works through a simple um, example. All right. So it's largely a heuristic example in a very small dimension, but hopefully it gets you some idea. Okay, so before we start, let's think about the big picture. Okay, why it matters, what's the key idea, and through this, I prepared a Q&A kind of exposition. So what's the problem TurboCon tries to solve? So LLMs store intermediate calculations called KV cache, the key value cache. If you remember in lecture 14a, the attention mechanism has key and value and query, and that takes a lot of memory. Okay. These are just vectors basically, it's in numbers. And the model processing a long conversation have to store millions of these vectors with hundreds of thousands of coordinates that's stored in 16-bit or 32-bit floating numbers that eats quickly the GPU memory, which is why the big techs in AI development have been buying up so many GPUs. So a single long conversation can consume 30 to 10 to 30 gigabyte of GPU memory just for the Kiwi cache. And well, there are similar problems in vector search databases, like in finance for semantic search over SEC filings, for example. There are many applications like this anyway. So we have too many high dimensional vectors and not enough memory, and we need to compress them. So what does actually TurboQuant do? It compresses vectors from 16 or 32 bits per coordinate down to 2 to 4 bits per coordinate, which is roughly 8 to 10 times reduction in memory. And the complex vectors are approximate, but the approximation is very good, good enough that an LLM produces essentially the same output quality, which is amazing. Okay, and the algorithm itself is very simple. It does two things to each vector: randomly rotate it, multiply by a random orthogonal matrix or rotation matrix, and then round each coordinate to one of the few discrete levels, like 4 levels for 2-bit or 8 levels for 3-bit. And that's the entire compression step, which is very simple. And and the rotation was basically innovation, and we'll talk about it in a second. Why are people excited about TurboQuant right now? Well, three reasons. First, it's online and data oblivious, meaning the previous compressions needed you first collect a batch of sample vectors, train a code book on them, and then use that code book to compress further vectors. It's like needing to study the last year's stock returns before you can compress today's data. TurboQuant basically skips all that. You can just compress each vector at the instant it arrives, like right there. Uh, no training, no codebook, no reference. Okay, so for KV cache, this is kind of essential because the vectors generated one at a time during the inference must be compressed right away, isn't it, to like the speed. And then second, it's a mathematical proof near optimality, meaning the authors prove actually the quality is within a factor of about 2.7 of the theoretical best that any method could achieve. And this is kind of a rare thing to have. Usually there's no such guarantee. And third, it is fast and simple. The entire algorithm is basically a matrix multiply, meaning a rotation matrix, followed by a table lookup, a quantization. No iterative optimization, neural network, nearest neighbor, whatever. So it's very simple. So what's the mathematical idea? I guess here's a warehouse analogy. Suppose you run a warehouse that ships packages of all different sizes, like in Amazon. Some are tiny envelopes, some are huge boxes, and some are medium, oddly shaped. You need to design one standard set of bin sizes for all sort of packages efficiently. If you design bins for small packages, then the big ones do not fit. If you design for big ones, then the small ones will rattle around the wasted space. And there's no single set of bins that work well for all shapes. Well, that's a problem, isn't it? So now imagine you have a magic blender that takes any package and redistributes the weight into exactly the same standard shape, say a sphere of the same total weight. After blending, every package looks the same shape-wise, just with a different total weight, which you write down on a label, okay, how much it weighs. So now you only need one set of bins designed for the standard shape, and it works perfectly for everything. Only if we had a magic blender. But it turns out for LLM we do. So exactly what quantum, TurboQuant rotation does. The packages are vectors with different coordinate structures like sparse, dense, skewed, whatever these are kind of things. And the magic blender is the random rotation matrix. And after rotation, every vector coordinates follow the same statistical shape, namely beta distribution, regardless of how the original vector was shaped, meaning sparse, dense, or anything else. We'll see this in a picture, so don't worry about it. And the total weight label is the norm, meaning the magnitude of the vector, stored separately as a single number. And it's just a single number, not much memory, single number. Uh, so one set of bins is the Lloyd-Max quantizer. That is basically how many bins we kind of have, and designed once for beta distribution and reused for every vector forever. So you just have to do it once, which is why you are ready when the vector comes in. You just already have done it. So it's a little bit of technical version there. Well, I guess I'll leave it with the heuristic here. Um, but there is a nice property of the beta distribution that when you multiply any unit vector by random orthogonal matrix, each coordinate of the rotated vector follows the same known probability distribution, namely beta distribution. Okay. So because the distribution is known in advance for the every vector, you can basically design one optimal rounding scheme, meaning quantization, and reuse it everywhere, isn't it? Um, the rotation matrix basically turned a hard problem into a very simple one. Um, so what's the finance analogy if you care? Suppose you need to compress daily stock returns data for 5,000 stocks. Each trading day gives you 5,000 dimensional vector. Some days market moves in a concentrated way. Few tech stocks move sharply while everything else flat, like a sparse return vector. Other days there's a broad macro event moves all stocks similarly, like a dense return vector. Knife compression scheme would need different precision settings for different market regimes, isn't it? When there's a sparse vector, you would concentrate the bins near where the trades were, and where it's flat, you don't need much bin, isn't it? But for the flat ones, you need bins across all kind of prices. The TurboQuant rotation makes every day look the same statistically. After rotation, concentrated tech-driven day and the macro-driven day both have coordinates drawn from the same beta distribution. One compression scheme handles all regimes equally with no need to look at the data first. So what we'll do is that we'll first define the vector and then separate the norm from direction, meaning the magnitude, and then the random rotation. We'll talk a little bit of what this beta distribution is and how it looks like, and then the Lloyd-Max quantizer, meaning how to design an optimal rounding scheme, quantize actual compression, reconstruct, meaning decompressing them and measure the error. And then there's some error in the inner product, and we see why and how to fix it. And then we'll just summarize it. And then we show that as you increase the bin, how the rate distortion curve looks like. More bits, probably less error, but how does it actually reduces it, the trend. And then let's compare against native quantization, okay? So what mathematical background you need, just basically linear algebra, basically, and we'll give enough heuristics, so hopefully you can just get something out of it. So quick note on rotation matrix. What does rotation mean? It's sort of like if you call back your algebra in high school, like this orthogonal matrix, like rotation matrix. If you rotate something, you had the cosine minus sine, sine, cosine multiplied, isn't it, from the trig class? Um, we do sort of something like this. It's orthogonal, but not exactly this one. There's even a more convenient one that's actually simpler, which is like the Hadamard matrix. This is also a rotation matrix. But it has like bunch of ones and minus ones, not even a continuous value, which makes it really simple. Um, the actual rotation matrix is actually in scaling by the norm here, which is square root of 4, which makes it this. Okay, and you can verify this. The R transpose of R is identity matrix, meaning that the inverse is really simple, isn't it? The transpose of the R is actually the inverse of it. So the algebra becomes really simple. Anyway, so that TurboQuant paper is here. And so here's the setup. So the visual overview, the pipeline here. So let's have like um, the thing here. So we get the infer vector and then separate the norm, rotation, and then scalar quantize, and then store the indices plus the norm, and then look up centroids, inverse rotation, rescale by standard norm, and then reconstructed value. So this is basically encoding and decoding process. Um, okay, so first the input vector. So we are creating small toy data set of 3 vectors. Um, in real life, of course, it will be, we use not just 8 dimensions, but in real life, it's like somewhere between 60 to 4,000 dimensions. So this problem is actually a lot more serious than what we show in this example. And we create just a deliberately very 3 distinct input vectors, sparse, dense, and skewed. Okay, and the good compression method must handle all these shapes well in the same quantizer. But if you think about it, like um, here, the sparse, like the rest are near zero, meaning that the day where only 2 stocks move and the rest stays flat, something like this. Whereas here it's all the stocks moved and something like this. Um, and the good compression must handle all 3 shapes well with the same quantizer, meaning where to slice the discretize the grid. Um, So the vector values themselves, look at the bar chart here that I created, okay? Here, so this is a sparse, this is a dense, every bar looks kind of similar magnitude, and here's like zigzagging, isn't it? Um, so that makes it difficult because this one we probably need to concentrate the grids here, whereas here we need to spread out the grids if the number of grids are the same. Then you basically have to spread it out all here, things like that, isn't it? Now separate the norm. What does that mean is that there is a vector, but we will have a unit vector and then multiplied by a scalar number, which is like the magnitude of the vector. And the analogy will be that if we say that 5 miles northeast, let's take the 5 miles part, which is the norm, separate, and just keep the northeast, the direction, in a unit vector. And the TurboQuant basically rotation matrix will just deal with this northeast, and then we can multiply back the magnitude later on. Okay, because saving this magnitude itself is just 1 bit, like 32-bit. It's very small thing relative to n-dimensional or d-dimensional coordinates we need to compress. Okay, so here's how this compression of that looks like on a 5, another one like 3, and then another one 4. So we keep that separate and then have this unit vector stored. So let's visualize it. So here are the 3 vectors. As you can see, V1 looks like this. Okay, and V2, the green one, had evenly spread out. But once you scale it by the norm, take out the norm, let's have all the magnitudes gives 1. You can basically make it like this. So they're all, the norm is basically 1. So now the random rotation, okay? So each coordinate follows after random rotation follows a beta distribution. What do you mean by this, isn't it? Um, so there's a lot of algebra here, but if we have that Hadamard matrix multiplied under the random way and the random sign, so here is basically the procedures that generate a random sign vector, -1 or +1 for each dimension, flip a coin basically, and then flip the signs and the z and then this s vector multiplied by this unit vector element wise, and then apply the normalized Hadamard matrix here. R is hd times z here. The Hadamard matrix is an orthogonal matrix that enters ±1, multiplying this as a norm preserving rotation, so the norm doesn't change. The random sign flips adds the randomness needed to make the rotation universal, meaning that distribution becomes beta distribution. Okay. And you should remember the same random signs and Hadamard matrix are used for all vectors. This ensures that the inner products are preserved exactly by the rotation, this thing here, for orthogonal R. Okay. So anyway, so how does it look like? Here's a visualization. So random after the rotation. Basically, here was a very spiking and then nothing here. Here's very uniform and here's like zigzagging. And what you can see here is that after the rotation, they kind of have most stuff here and small magnitude here, most stuff here, small magnitude here. It, if you see that, it kind of became something similar kind of looking. Okay. And what is the beta distribution? So what does it do? So we basically experiment how the random rotation and the beta distribution looks like. So I actually did a plot here for 50,000 random coordinates being basically rotated and then do a histogram of it. That is the histogram, and the red line is the beta distribution. They kind of line up, isn't it? Even in the CDF, if it's more. And the more you increase the dimension, the more sharper peaked it becomes, just as a property of the beta distribution. And then you could just, if you want to cut a grid, put a grid, you put the grids in here, isn't it? So for very high dimension, so you can concentrate the grids here and become more accurate. Whereas very low dimension, it's spread out, so you actually have to put the grids all over the place. Okay, so once you have transformed it into this kind of distribution, what do we do? Now we actually have to decide where to put the grid points, isn't it? And there's a process for beta distribution. It's called Lloyd-Max optimal scalar quantizer. So if it's one bit, you have 0, 1, like or minus 1, 1. It's two levels. If you have 2 bits, you have 4 levels, isn't it? And 3 bits, you have 8 levels, 4 bits, 16 levels. So what do we need to do for this quantization is that you need to have the boundaries, where from where to where is the first spin and then the next spin and all this. And then the centroids, where's the center point here? Okay. So, and you iteratively find it. So how it looks like, um, basically, if it's a full bin, then you can cut it here. You can see that at the hump, the bins are more tighter because more mass is here. You want to be more accurate here, whereas the distribution of mass is small, then you can have a wider grid here. Likewise here, isn't it? So this is how this works out. So this is the quantization. And once you know the beta distribution, this is all the same, isn't it? And the dimension dictates it. And what we just do here is that if there's an input vector which just happens to be falling here, and the star is the centroid of this bin, so it happens to be falling in here, that input vector, and the centroid is here, then the error is basically measured here. And these bin grids are measured in a sense that this beta distribution, wherever randomly comes, the errors are kind of minimized by from the centroid. That's how the bins boundaries are determined in the centroids. So quantize the rotated vectors. Okay, so for here we quantize them, and then so our original, so the quantized one, the rotated ones are being quantized here. Um, the, and the rotated coordinates. So here basically it falls nicely in this 2-bit or 3-bit, in the 3 or 2-bit, isn't it? For each vector, vector 1, vector 2, vector 3. Okay, uh, and yeah, and so this red line distance would be the error, isn't it? And now you can reconstruct, meaning the inverse is on R transpose is the inverse. That's a property of the linear algebra of the beta distribution, also on a matrix. So you can basically now you have centroid made it quantized. So now you actually carry only these discrete values. You forget about the blue bars and just keep the red axis, which can only take in let's say 2-bit, it can only take 4 values. The Y level of values are like 1, 2, 3, 4, isn't it? So you need to only remember 4 levels. And for 4 levels for each vector dimension, now you invert it um, by matrix multiplying the R transpose. And the resulting thing, if you look back, multiply the magnitude back, the actual bar, original bar, and the quantized bin reproduced approximations are pretty good, isn't it? Um, yeah. So, but there is one bit problem in that although the levels are fairly reasonably accurately predicted and approximated by these centroids, um, if you do the dot product of these two vectors, they tend to be a little undervalued because of the rounding errors for the centroid. And you can see that the 45-degree line would be the inner products MSE, but you can see the slope is slightly less than 45 degree, meaning the inner product is little less than 1. So, so what do we do then? We basically, the trick here, there's a correction algorithm after quantization and all that, is that you basically compute the error. You basically compute the error and log the direction of where the error is, okay? Just a sign, like this is positive, this is negative, not the magnitude, just the sign. And just the sign, there are ways to make corrections. Um, Basically, the residual is the true value minus the quantized value. And if you just keep one more bit for these residual signs, like whether it was +1 or -1, then you can do a fairly accurate bias correction to get the inner products fairly accurate. Okay. Um, yeah. Um, Yeah, so that's basically a trick. And the reason why it helps us intuitively is that the underestimated inner product is basically if one number, there are two numbers multiplied to make an inner product, isn't it? Where each numbers are basically rounded up or rounded down. This looking at the residual sign, you can see whether both were rounded down, both were rounded up, or the one was rounded up and one was rounded down. In a law of large numbers, if you have many dimensions, those errors you can correct to converge the arguments can be by law of large numbers to converge to the true inner product. So you can basically have means to correct for the inner product. Okay. So this whole process is being looked at, and here's the TurboQuant, the bits per vector, and you can see that the original is like very large, but the compressed one is this tiny, isn't it? Um, and for the sign and the indices and the norm, so you can basically compress it fairly a lot by a lot, but still um, got a fairly accurate computation of the inner products. So as you increase more bits, have increased the dimension more bits, of course, like in LLM, like 4,000 dimensional. Of course, this kind of inner product error gets smaller, the mean square error gets smaller. What, but I guess if you have like in 4096, if you have one more dimension, the impact is probably much smaller than if you had just two dimension and it becomes a three dimension, the impact is much larger. So how does the trade-off look like? Here it is. Bits per coordinate, 1 bit, 2 bit, 3 bit, 4 bit, and this is in a log scale. You can see that from 1 bit to 2 bit for each coordinate, it drops from 0.92, the mean square error, to 0.19, like wow, 1/7. Uh, okay, but then from 2 to 3, it's 1.15, so it's 1/3 reduction. And then from 3 to 4, it's basically just half. You see the idea. It's kind of the additional bit, the bang for a buck gets smaller, isn't it? And for the inner product error too. It decreases, but the impact is much smaller. So, which means that you don't need that many bits, frankly, because the marginal impact of having additional bit after a few bits is actually not that much. So, and you get fairly accurate. Okay. And finally, can we compare against the naive quantization, meaning just place the grid evenly, like D8 or T128? How does it look like? And you can see that as we increase the number of bits per dimension, of course, naive grid or TurboQuant gridding basically decreases, but you can see always TurboQuant stays below, isn't it? And this is for 8-dimensional kind of problem. The gap is actually still modest. If you actually have the dimension of a 128 dimension space, you can see it's like from 10 to the 2, like 100, and here is like zero point 0.1. So it's 1,000 times difference, isn't it? So you can see that the TurboQuant is actually fairly accurate. The mean square is like very much smaller than a naive discretization, which now you can see that with just these few points, you can actually do it fairly accurate calculation, um, and you don't need to spend so much GPU memory. So this was basically the message that the TurboQuant paper was trying to convey. Okay, so this was a brief summary of why TurboQuant mattered and what it kind of does in a heuristic example. Um, and hopefully now you can have a better understanding of what this is. Thank you for watching this episode.